Hello students, in this video we'll see two examples of using the intermediate value property of continuous functions. Here's our first example. Let's show that the equation 1 minus x cosine x equals sine x has a solution on the interval 0, 1. And so we're going to use the intermediate value property. So notice that f of x, which is the function 1 minus x cosine x minus sine x, is continuous on the closed interval 0 to 1. And so let's plug in 0 to this function. F of 0 is going to be equal to what? F of 0 is going to be 1 minus 0 cosine of 0 minus the sine of 0. And that's equal to what? Well, the cosine of 0 is equal to 1, so f of 0 is equal to 1. Let's look at f of 1. F of 1 is equal to 1 minus 1 cosine of 1 minus the sine of 1. And of course, this first term over here, this 1 minus 1 is giving you 0, so this is just negative sine of 1. Okay, so what do we have? We now have the following. We have that f of 0 is greater than 0. And f of 1 is less than 0. And so by the intermediate value property, between 0 and 1, so the function starts above 0 and goes below 0. So by the intermediate value property, we have f of c is equal to 0 for some c in the open interval 0 to 1, and that value of c is going to be a solution to this equation. So that's an application of the intermediate value property. Let's see one more example of this. Example. Let's show the equation e to the x equals absolute value of p of x has a solution for any polynomial p of x. Okay, so pick any polynomial you like, take the absolute value of that polynomial, and that will intersect the graph of e to the x at some real number. Okay, and so here's the idea. The idea, of course, is to form a continuous function. So I'm going to form q of x, which is p of x absolute value times e to the negative x. Now, it's important to note that the absolute value of a continuous function is still continuous. So I have a continuous function p of x, a continuous function e to the negative x. This function over here is continuous. So we're in good shape there. It's a continuous function. And furthermore, what can I say? What's the limit as x approaches infinity of q of x? Well, as x approaches infinity, this term over here, this e to the negative x, is approaching 0, right? And it's going to 0 faster than any polynomial can go to infinity. So this is going to what? This is going to go to 0. Whereas the limit, as we go to negative infinity, the limit as x goes to negative infinity of this function q of x, well, as x goes to negative infinity, this e to the x is going to infinity, and it's going to infinity times something that's either going to infinity or negative infinity. So this thing is going to go to infinity. So this will go to infinity. So we have a function q that's continuous. As you go to positive infinity, you're going to 0. As you go to negative infinity, you're going to infinity. So the graph looks something like this. So here we are. Here's our x-axis. Here's our y-axis. And as we go to infinity, we're going to 0, and we start off at infinity. So our graph has to look something. I'm not actually exactly sure what it's going to look like, but it has to do something along those lines. Now it's up at infinity. It's down at 0. So somewhere in between there has to cross 1 by the intermediate value theorem. So by the intermediate value theorem, by the IVP, intermediate value property of continuous functions, q of x is equal to 1 for some x. And if q of x is equal to 1, what does that say? That says that for that value, for that, we'll say x tilde, for that x tilde, that would say that p of x tilde, e to the negative x tilde, is equal to 1, which is equivalent to saying the absolute value of p of x tilde is equal to e to the negative x, e to the positive x tilde, and therefore that x tilde is the solution of our equation by the intermediate value property. Thank you very much.